So good morning everyone, my name is Lawrence and I've been working with the triathlon cycling data. My topic was describing and classifying the variability in cycling race power output. So the main motivations for this variability analysis was, in particular for triathlon, it is known that a greater power output variability during the cycling component of the race could hinder running performance. Some other motivations were to classify the type of course based on the variability analysis, the tactical style, the type of race, so a time trial, cycling track race, things like that, and also other physiological factors such as fatigue patterns and optimal performance patterns as well. With the ultimate goal to be informing training decisions to optimize performance. But before we do this, we actually need to classify and describe power output variability. So some initial statistical analysis methods included ANOVAs, linear models, linear mixed effects models, and principal components analysis. These were used to gain more of a feel for the data, but they didn't actually help with actually analysing the variability of power output. If I just skip to this slide. So this was one of our initial plots, just to see how cadence varied with power for each of the 5 races. There were 5 races in the data set. And you can sort of see from this plot that most of the athletes held around 95 cadence. So that might be due to how they've trained and things like that. So the statistical methods that were used to actually understand the power output variability included taking the first order differences, ACEMS models, and hidden Markov models. So the first order differences were used to illustrate the magnitude of the change in power output at a particular point in time, and hence the power output variability.
Can you explain what a first order difference is?
So it's just taking the power at 2 time points and just taking the difference of that. So we've got, on the x-axis, we've got each of our difference points, and on the y-axis is how big that difference was. So we can see sort of at the start of the race, we've got larger differences between our power output points. So we could say there's a bit more variation in the start and the end compared to that middle section there. So ACEMS models we use to create moving averages of power output for each race. The moving average is a smoother curve than the raw data and provides information about the overall trend. And we took a moving average after every minute during our 1-hour race. Another method that we used was the hidden Markov model. So we used this to understand the power output variability by classifying power ranges or states. So one of the states was centered around about 200 watts, so it would range probably from 150 to 250 watts. So they're assumed to follow a Markov process where the states are not observed or hidden. So this is particularly useful for this data set since we haven't classified power ranges at the start, so we can't really see them. So if we have a look at the second from the bottom, that's our trend line for race 1 using the ACEMS model. So on the x-axis we have time and y-axis we have power output. So we can see towards the end of the race the power output was significantly lower compared to the first third of the race especially. So this is the plot for race 1. Here in blue we have the raw data. As you can see, it's very hard to actually get anything out of it. Looks pretty random and noisy, but if we put the pink plot on top with the moving average of every minute, we can start to see something from it. for example, at about 115 to 120 minutes, the athlete was at a significantly higher effort, and probably at around 145 minutes, there was a significant drop for a fair amount of time as well. So here we have race 4, and we can see even the moving average line is has a bit more variation in it. So we can draw from that race 4 has a higher power output variability than race 1. So onto the hidden Markov model. A highly variable race in terms of power output would be categorized by frequent changes in the states we classify. So a sprint would be classified by the state that explains the highest power output. So on the left-hand side of this table, we have states 1 to 5, with state 2 being the highest, centering around 430 odd watts, and state 5 centering around 0 watts when the athlete is not pedaling or going downhill. So this plot here explains the distribution of these states throughout the race. So state 2, which was the highest state, is in that orangey colour. So we can see at the top of those peaks, we have that orangey colour there. So now we can clearly see the distribution of those sprints throughout the race. So a high variability in a race would be very colourful, lots of changes in these states, compared to a low variability, which would just be almost one colour, staying within that one state throughout the race. State 4 was centred around 200 odd watts, which was the average power output for this race. And you can see that's that blue colour centering around the middle of that line there. And we also have a frequency of points in each state. So state 4 was the average power, and that has the most frequent amount of points in there. For a highly variable race, you would see almost the same frequencies for each of these states, but a low variability in a race would have almost all the frequency in just one of the states, so they're staying in one state throughout the race. So for future work, the next step would to validate this hidden Markov model as an appropriate statistical method. And we would also have a bit of a further look to see if there are other statistical methods that could even do a better job. It would also be helpful to include elevation and course map details, and controlling for these variations in power output creates scope for future projects, including the analysis of how drafting or tactics affects power output variability and how power variability affects running performance in a triathlon. That's about it. Are there any questions? Yep.
I like the way you put it together. It's nice. You paint a nice story and picture. So even though it's my data, I knew exactly where you were going with it.
Yeah.
The bit that I sort of didn't quite get my head around is the 5 states that you use there.
Yeah.
How do you arrive at determining the states?
So when in R, we put our variables into the model and we specify how many states we want. So at the start, I just started with 2 states and I was getting like 200 and 240. So that didn't really tell me much, and then added more and more states till I got something that I thought explained the data set. So I especially wanted something that was close to 0 because a lot of points were at 0.
Okay.
And I also, so when I got to 5, I thought it explained the data set quite well. But what's different about the hidden Markov model is that these states would be different for each particular race and each particular person. So if I applied that same model to a different race, I might get different numbers if I specified 5 states as well. So if, say, an amateur cyclist had done that and their peak power was only 200 watts, these states might only range from 0 to 250 if I specified 5.
Does it take into account the speed and the cadence as well in making those states? Like,
Yeah.
Find the best match of each of them.
Yeah, so I added those as covariates as well.
Yeah, cool. Because I was looking at it and there was like ones that were like blue and then there was orange and they looked almost identical in terms of power. So that must have been differences in terms of the cadence and the speed potentially.
Yeah, so you can, by that plot, they're not as clean cut as power ranges. They're a bit more fluid by the...
Definitely.
Yeah.
No, that's really cool. It'd be awesome to see like a 3D plot of that almost, to be able to go, this is what's happening with the cadence or something on the outside. That'd be great.
Yeah.
I guess that's the interesting thing about these models is that, okay, we're trying to estimate what is the hidden state, like what is the state of the athlete, how they're able to perform or something like that. And it's like, well, we can learn these things from data, and do they have meaning physiologically?
Yeah.
Do they make physical sense?
Yeah.
So we're sticking with the 5 states. Say for that particular athlete, we had physiological power. There was reasons that 0 to 100 watts might be a training zone. It's an aerobic zone. It's a low physiological load, but 500 to 6, or let's say more realistic, 700 to 1,000 is a really high physiological range. Is there a way of tying that data together to come up with a stress factor?
Well, yeah, so I think based on these states, anything over 400 would be your more stress states. If we added more states, we would get more ranges. But if I added a 6th state, I think I got another one between 200 and 300, just because there was more points.
So maybe think of another one. So is there a way of looking at how long they spend in each burst of state 2 and how far apart those bursts are from using this sort of model?
Yeah, I think there would be a way to do that.
Your critical power W prime probably at that point. You've got a critical power W prime indicator for each of those guys. That's the model you're probably looking for there in terms of your fatigue and your reconstitution of work effort type stuff.
Yeah, well, that's sort of what I'm thinking. I'm thinking a way of tying that to that model that we can create from collecting test data to what's actually happening in a race, and then giving it a score.
Yeah, definitely.
And so something you can do with these, well, I guess I'll be extending the model somewhat. In a state space model, then you can start to associate with,
Can you speak up a bit?
right, sorry. So, so like almost into a network model then. So it's not just about here's the measured value and here's the hidden state, but you can have other variables, other states, including these training zones, the aerobic zones, anaerobic zones.
Yep.
And that kind of thing. Time, or what's the relationship between that and performance. But also, I guess you could also think of it potentially, just ideas. So maybe it's about energy. How much energy does the athlete have? Otherwise, they could just keep hitting the high
Exactly. Yeah. So, if we're looking at the purple bits, notice there's gaps between each of them. Hold on, I've got that. Purple was the high one, wasn't it? No.
The
red.
Yeah, the red. Yeah.
Yeah. So it's interesting to know whether there's a critical distance between how frequently a state 1 could occur. if we had enough data, if we associate state 1 with their, like you're saying, a physiological model,
Yeah.
and it's your anaerobic capacity, can we locate in there, it shouldn't be able to occur any more than, 30 seconds apart or 2 minutes apart.
Yeah.
And if it does, then that's a point in the race that's been very critical, and it may have been the point where the outcome of the race turned when they've had to exceed their limit.
Yeah, definitely. Yeah, and it'd be a combination of the duration of those sprints as well as the frequency of them as well.
Well, yeah.
Because the longer you sprint, the longer you're above threshold, the more you're eating into that capacity too. So you can eat it all up in one sprint if it's a 5-minute sprint.
Yeah.
I mean, that's not necessarily going to happen in a triathlon race, but theoretically,
Yeah, I guess.
someone just goes off the front, they're not going to stay off the front the whole time.
Correct.
Yeah, they're going to blow up at some point.
But hidden states sort of take that time out by defining the state, if I'm following it correctly. It sort of takes the two, it's a hybrid of the two, duration and power.
Yeah.